In this module, we'll discuss the comparison of two population means where each sample is actually a pair of measurements, one from each population. We'll see that the hypothesis test and confidence intervals for this situation are actually more similar to those of the one sample test than they are to the two independent samples test. Paired comparisons are widely used and a useful way to decrease type 2 error, as we'll see in a minute. Paired comparisons are also an example of blocking, and you'll see many more uses of blocking if you take a class on experimental design. Here's an example. Suppose we have two different materials that we make a sole of a shoe out of. We would like to test the two materials under realistic conditions. We collect 10 data points on the wear of material A and 10 data points on the wear of material B. Here are the results of the 10 measurements of wear for each of the 10 shoes tested. Are the two materials different? How do you think the 10 data points were collected? 2 shoes on 5 boys for each of the two materials for a total of 10 boys? 1 shoe on 10 boys for each of two materials for a total of 20 boys? How would you set up the experiment? As it turns out, boys tend to differ quite a bit in the amount of activity and the surface on which that activity takes place. So there's a lot of variation in the amount of wear from boy to boy. What was actually done was each boy was given 2 shoes. One was made with material A and the other with material B. Each pair of shoes, or experimental units, was worn by the same boy at the same time. How do you think the experimental condition A or B was assigned to the shoes? Well, it might be easiest if we made all the right shoes from material A and all the left shoes from material B, but that might confuse the results. What if the boys tend on average to wear out their right shoes more than their left? The difference between the shoes could be due to something like that rather than the different materials. We should probably randomly assign the materials to right and left and probably balance over the 10 boys. Here's that same data that we saw graphed before, but now it's organized to show the 10 boys and the wear on the shoes that each boy wore. Now how would you make the comparisons? Well, 8 out of the 10 boys had higher wear numbers on material B. The 2 boys that didn't had numbers that were very close. Is there another way to look at this? Here's the formal setup of the hypothesis test. So far, it just looks like 2 independent samples hypothesis test. We could just conduct the test as before, but that would ignore the fact that the same 10 boys wore both kinds of materials. Instead, let's create a new column of data. Let D be the difference between material A and material B. It really doesn't matter which is first and which is second, but you do need to keep track of it. Now the new random variable d sub I is assumed to be independent and identically distributed as normal. Here the display on the top shows the data not taking into account the pairing. It doesn't look like the two materials differ very much on average. The second display shows the difference between material A and material B for the 10 boys. Here it's pretty obvious that the two materials wear differently. So what test statistic would you use to see if the difference in wear between the two materials is statistically significant? Turns out we already have a test like that, the one-sample t-test. If we apply the two-sided one-sample t-test to test the null hypothesis that the difference is 0, then we come up with a t-value of minus 3.35, which is less than the t-critical value of minus 3.25, hence we reject the null hypothesis. Because this is just like the one-sample case, all the same ideas apply. But here the sigma is the standard deviation of the differences, and the results are not complete. The results are completely correct only if sigma is known. If not, as is usually the situation, the required n is a little larger. The confidence interval for the difference of the means when the data is paired is again similar to the one sample case formulated on the D's. Paired comparisons is the simplest example of blocking, which is a more general term for the grouping of experimental units. As we say in the example, pairing can increase your ability to see the differences, or in other words, reduce your type 2 error. If you take a course on experimental design, you'll see more examples of this blocking technique to increase power or decrease type 2 error. Sometimes pairing or blocking is not useful. Under what circumstances would pairing not decrease the type 2 error? I'll let you think about that one. Here are some of the things you'll be expected to be able to do as a result of viewing this module and completing the associated assignments.